Swayam Prabha. Digital India. Educated India.
Okay, so we will talk about universal hashing. So, this is coming from a what is the weakness of a hash function. So, this is a fundamental weakness of a hash function. Hash function is a function from any bit input to a fixed bit output. So, domain size is very much bigger than the codomain size. So, there has to be collision. So, suppose suppose some company like Microsoft or they made a competition to get a hash function. So, you develop a hash function, your friend develop another hash function, and both wants to win the show. So, you both submitted your hash function to the Microsoft. Then what Microsoft will do? Microsoft will give your hash function to your friend and your friend hash function to you, and ask to find out for the input where it will perform badly. So, there has to be certain input where it will perform badly. So, there are your friend can get such input k or x y pair such that, so this is the, so always it is possible because it is a fixed, the codomain size is very less and domain size is more. So, your friend can always get a key, the bad portion of the key where everything is mapping to a particular slot. So, more collisions are there, and your friend will report to Microsoft, hey, this is the set of input where my friend's code is gone, I mean it is colliding to the particular slot. So, that is always possible. If you have time, you can do that. So, that is a fundamental weakness of hash function. So, to avoid that, what we do, we can choose the hash function randomly at the runtime. So, that is the idea of choosing the universal hashing. So, in universal hashing, we choose the hash function randomly at the runtime. So, that nobody will come with some input where your code is performing badly, like it is more, because you do not know which random variable will be chosen. So, depending on that, we will come to the construction of such hash function. So, let us formally define what is universal hashing. So, suppose this H is a set of all hash function or collection of hash function, set of all hash function H from U to this. So, the H is this set. Okay, so, H is basically set of all hash function which is from U to this. So, this is our collection. Okay. Now, among this collection, and suppose we have a bad portion. So, bad portion, how we define the bad portion? Bad portion means if you take any two key, x y, and if we choose the hash function from this bad portion, then there has to be, then these two will collide. So, that means bad portion is set of hash function from this collection of hash functions such that h of x will be h of y for any pair of keys, for any x y belongs to U cross U. So, this is the bad portion. So, that means the collision is guaranteed. If we choose our hash function from this, then if you take any two keys, then they will be colliding. Now, if the size of this bad portion, if the cardinality or the size of this bad portion is basically size of the total by m, that means m is the slot number of slots. So, 0 to m minus 1 is the number of slots. So, if the size of this, if there are 1 by m fraction of the total set is basically bad, then we called this collection is universal collection of hash function, and if we choose a hash function randomly from this collection, that is universal hashing, and it is a good choice. We will discuss that why it is good. So, this is the universal collection of hash function, and why this universality is good, that we will talk about. So, now the question is why universality is good. I mean, why this collection is good? That means, if you take a hash function randomly from this collection, why this will perform good. Okay. So, this is because if we just denote, if we just write a theorem like this, so let h be a hash function chosen randomly, h be a hash function chosen uniformly at random, from this from a universal collection of hash function, universal set h of hash function, okay. And then the expected number of collision with x, if for a given x, then for a given key x which we are searching, say we are searching a key. So, then the expected number of collision with this x, is less than n by m, which is the load factor, and that is good. So, if we are searching for a key x, now if it is expected number of collision is alpha, that means it is the basically the load factor of the table, then it is a good news. So, we have to prove this. So, if we choose a hash function uniformly at random from a set of hash function, then this is the expected number of collision with x. Okay. So, this we need to prove it. Okay. So, to prove this, we will take help of what is called indicator random variable. Let us denote Cxy is 1 if Cxy is 1 if h of x equal to h of y. We take two key xy and we denote this random variable value is 1 if they are colliding, 0 otherwise. This is how we define the indicator random variable. Then what is the probability that Cxy is 1? This is basically 1 by m, because we have seen if we take any two keys, then we are choosing the hash function uniformly at random from this collection. So, it is basically there are total, this way we can choose, and if we choose that hash function from that bad portion, then it will collide, and that favorable case is this. So, this is basically 1 by m, simple classical definition of probability. So, this is 1 by m, and so what is the expectation of this? So, the expectation of this random variable is basically 1 into, it is basically binomial random variable, plus 0 into probability of Cxy is equal to 0. So, this is basically 1 by n. Okay. Now, we are looking for a given x, we are looking for the expected number of keys collating with x. So, that we denote by C of x, the number of keys collating with x. So, that is nothing but C of xy, where this y is belongs to key space, I mean the key space whose size is n. So, this is basically n minus 1 other than x. So, if you take the expectation both sides, so this is basically expectation of C of x y. So, y is belongs to minus x. So, this is basically m by so n minus 1 by m, which is less than n by m alpha. So, this is the proof. So, which is basically 1 by m. So, this is good news. So, universally it is good. So, if we have a such collection where the bad portion is just the 1 by m fraction of the total collection, then if we choose a hash function uniformly at random from this collection, then that hash function performance is good. That means, it will distribute the key uniformly. That means, load factor will be preserved. Okay. So, next we will talk about how we can construct such a hash function, the universal hash function. So, this is the construction, one example of universal hash collection. This is one example of, or how to construct a universal example of universal hash function. Okay. So, here we divide the key. So, we have a long keys, we divide the key into R blocks K1, K2, K3, Ki, such that each of Ki's are between 0 and m. Okay. So, each of these block size is maximum m, m is the number of slot. So, this is how we divide. So, maybe last block we have to add something to make it m size. So, if m is 2 to the power r or m is 2 to the power say l, then each of this block is l bit. Okay. So, now what we do? We take a vector a randomly, a1, a2, a3, ar, and this is ai's are also lies between this, and each is ai is chosen randomly, uniformly at random, So, this is a constant, we randomly choose this constant and we fix this constant. We choose these ai's, then we have this vector a and we fix it, that is a constant now. Now, we will use this for this hash function to construct a hash function, and that hash function is denoted by h of a, because this will depend on this constant a. Okay. So, this h of a k is basically summation of ai ki I is equal to 1 to r mod m. This is basically the inner product between a vector and this is the key and this k vector. So, key is basically k1, k2, kr, and a vector is basically a1, a2, ar. So, we are just doing the inner product between a vector and k vector, and we obviously have to take the mod m, because our slot size is 0 to m minus 1. Okay. So, this is one construction of hash function. Now, we need to prove that this collection, I mean collection means if you vary a. So, a is chosen from this way. So, if you vary A, we are getting different hash function. So, varying A means we are varying this A1, A2, AR, these are chosen randomly. So, this will give us a collection. Basically, our collection is H is basically H of A collection. So, A is varying. So, this collection, so this is chosen randomly. So, this collection we have to prove that this is a universal collection. So, how to prove this? So, what is the cardinality of this H, this collection? This H is basically, so we have the choice for AIs, each AIs are taking value from 0 to m minus 1. So, this cardinality of this is basically m to the power r, because it is depend on. So, this is A1, A2, AR. So, each this can be MOS, this can be MOS like this can be MOS. So, m into r times. So, this is basically m to the power r, this collection. Okay. So, now we need to consider the bad portion. So, bad portion means the where collision is there. So, that means we take two key x and y. Say x is x1, x2, xr, x1, x2, xr dot dot dot, and y is say y1, y2, yr. Okay. So, now we want to, and xy is not equal. So, if xy is not equal, we can assume one of this digit is not equal. So, without loss of generative, we can say x1 is not equal to y1. Now, we take, actually we are calculating the cardinality of the bad portion. So, we take h of x equal to h of y. So, h of x is nothing but summation of ai xi mod m is equal to summation of ai. So, this is a, this is a, ai yi mod m. So, if this 2 is under mod m, so that means they are congruence 1 to r, I is equal to 1 to r. So, that means they are congruent. So, that means ai xi I is equal to 1 to r is congruent to summation of ai yi I is equal to 1 to r mod m. So, they are okay. So, now we want to simplify this. We take this here, yeah. So, we take this we take this side. So, summation of, so a1 we take common x1 y1 plus summation of ai xi minus yi, this I is from 2 to r, this is congruent to 0 mod m. Okay. This is congruent to 0 mod m. So, now we take this side. So, a1 x1 minus y1 is equal to minus summation of ai xi minus yi I is equal to 2 to r mod m. Okay. So, now we take, now we know this x1 is not equal to y1. So, this means x1 minus y1 is not equal to 0. So, we can take the inverse of it. So, a1 is basically is congruent to minus summation of ai xi minus yi I is equal to 2 to r into x1 minus y1 inverse mod m. So, this will give us no choice for a1. So, that means, so if we have a1, a2, ar, so once we choose this, then a1 is fixed by this relation. So, that means this can be choose MOS, all this can be choose MOS, but only thing this can be choose one OS. So, this is total number of such collection is, this is the bad collection, is 1 into m into like this. So, this is basically m to the power r minus 1, which is basically m to the power r by m. So, this is basically cardinality of h by m. So, this is the size of the bad portion. So, that means it is a, so it is the bad portion is 1 by m fraction of the total portion. So, this collection is a universal collection. So, this is an example of universal hashing. Now, if we choose a hash function from this collection, that is called universal hashing. Now, let us analyze about the so how we can yeah. So, this is one construction. Now, let us talk about what is called perfect hashing. There we will use this universal hashing, universal hash function. Okay. So, in perfect hashing, what we have, the problem is we have given a set of keys, n keys. This is a static arrangement. We have given a set of n keys and we need to create the table, so that there will be constant number of I mean the search will be in constant time. For searching, we should not take more than constant time. So, that is the idea. So, this is a static arrangement. So, that means we are not allowing any new member to join, any new record to be joined, or any record to be deleted. So, basically we have n keys. So, this is the key pool. We have n keys and we have to arrange these in a table in such a way that the searching will be in constant time. Okay. So, this is basically a two level hashing. So, what we are doing? So, in the first level, so there are n keys. So, in the first level we create a hash function. We choose a hash function. This could be a universal hash function. So, we have a origin hash function. So, we apply these are the keys. So, we apply this hash function on these keys. This is the first level hash function. So, this is 0 to m minus 1. This is the level 1 hashing. Okay. So, if we do that, there will be collisions. So, suppose at the nth level, so suppose at the ith slot, there are ni number of keys are colliding. So, at the ith slot, ni number of keys are colliding. So, what we will do? We will then, we cannot store ni keys over here. So, what we do? We will go for the second level hash table. So, here we will have a table whose size is ni square, if ni keys are colliding here, and this is a second level hash table. So, this is ni square, and for second level hash function we need to store the hash function over here. So, that we can store by just storing the a vector. Okay. And then this is basically h of a we apply on this, and which will put it here, which will give us which will map these keys into this table. So, let us take some example. So, this is the idea. So, this is say we have some set of keys and we have the first level hash function dot dot dot. Now, this is our n keys. Okay. Now, suppose here we have some hash value. This is only one say, but suppose here in this table we have two keys which are colliding, say 311, 412. Two keys are colliding here, say in the first level. So, what we do? We need to create a second level hash function, second level hash table of size, since two keys are colliding, of size 4. So, this is 4, this is the size of the next level hash table, and then we need to apply, we need to have a value. So, say a could be say 51. So this is the A value. A will give us the hash function because we need to have the hash function. So then we apply this H of A. So this is maybe 311, this is 412, and these are empty. So this is the first level hash function, and this is the second level hash function. So this is 0, 1, 2, 3. So H of 51 of 311 is equal to 1. H of 51 of 412 is equal to 3. But H of 311 is equal to H of 412. Say this is a 0, 1, 2, 3 slot. This is basically 3. So they are mapping. Now suppose we have another slot which is having 3 keys are collating. Then suppose these 3 keys are say 590, 611, 712. These 3 keys are say collating in here. So in that case we will put a table of 9 slot 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We put 9 slot for the second level hash function, and we have to have a say this is a 69. So this is a 590, this is a 712, and this is a 611. Okay. So these are all empty. So that means at the first level all these points are collating at here. So say this is a 10 slot. Okay. So that means H of 590 is equal to 10 is equal to H of 712 is equal to H of 611. These are collating. So three keys are collating here. So this is in the first level. So for second level we need to have 3 square, 9 table size, and we need to choose a hash function that is also uniformly we are choosing from the universal hash function, and that A value, A vector is basically we choose some A vector that will give us the hash function. So that means H of 69, this is the A value of 910, 590 is 1, H of 69 of 712 is equal to 4, H of 69 of 611 is equal to 7, sorry 9 slot, so it should be 0 to 8, okay, 7. So this is the way we just have the second level hashing. So in the second level the collision we can guarantee that is nil, because suppose we have 3 keys and we are having 9 slot. So 3 keys are distributing in the 9th slot. So if we have n keys, we are distributing in the n square slot, then the number of collision is even less than 1, that we can prove. So we have huge space to distribute the keys. So the collision will be less in the second level. We can guarantee that on an expected second level there will be no collision, even less than half collision will be there. So how to prove that? So suppose this theorem is telling, suppose there are n keys and there are n slots are distributing, this is in the second level analysis, then the collision is, number of collisions should be less than half, we want to prove. So then if we take 2 pair of keys, what is the chances of they will collide? The probability of collision is basically expected number of probability of collision is 1 by m. This is because we are choosing uniformly. Now there are n C2 number of pairs. So this is the expected number of collisions. So this is basically n into n minus 1 by 2 in n square. So this is less than half. So even we cannot expect 1 collision. So expected number of collision even is less than half, because we see here we have 9 slot and we are storing only 3 keys. So collision is nil actually. Okay, if our hash function is uniform hash function, it will distribute the key uniformly among the slot. Okay, now another thing, we should analyze the storage. intuitively it is taking the, we are taking huge number of storage in the second level. In the first level storage is m, size is m, and in the second level intuitively we are having the n square. I mean, if the ni is the number of keys colliding in the ith slot. So, we will do the storage analysis. Storage is basically m for the first level, and the second level is ni square, I is equal to, we have 0 to m minus 1. Okay, so this is basically, ni is basically number of keys going to colliding to ith slot. Okay, then if you take the expectation of the storage, then it is basically m plus summation of expectation of ni square. Okay. Now, this analysis we can, this is a similar analysis if you are familiar with some sorting algorithm which is called bucket sort. If we have n keys, we are distributing into the buckets, and if we denote this xij is basically 1, if the kj is going to this slot, ith slot or ith bucket, 0 otherwise, then the basically ni is basically summation of xij, j is running from how many keys are there, 1 to n, something like that. So, squaring means squaring of this. If you take the expectation, this can be shown that this is also order of m. This analysis is there in the any algorithm book. This is the bucket sort analysis. So, the storage is basically again order of m. So, we are not really using the extra memory much. So, this is reasonable order of n m. Okay, thank you.